Thank you. Well, I wasn't quite expecting that introduction, but thank you very much. So yeah, Tomek has just spoken about some of the things that we do to be able to process large amounts of data cost effectively. What he didn't say is there's actually an even cheaper way that we can save even more money on this, which is simply not to gather the data in the first place. But there's a reason we don't do that. Hopefully it won't come as too much of a surprise if I say that we really value the insight that we can get from analytics and the power of making decisions in a data-driven way. But analytics has a flaw. It can only tell you about things that have actually happened. So what if you want to know about a system that doesn't exist? Where do you start? So if you're like most people, you probably start with ChatGPT, but where do you start if you want something that's a little bit less vibes-based? You probably see how far you can go with analysis. So you start by looking at the range of data that you've already got. Maybe you break it down into different pieces. You try to reason about what will happen. But what if the system's just too complicated? That's where simulation comes in. So by simulation, I mean building a model to represent a system, and then you analyze that model, and you can use learnings from the model for real-world decisions. So when do you use simulation? You use simulation for complex systems where the interesting behavior is emergent and can't be reasoned about analytically. So complex, what do I mean? I mean that the behavior is non-linear. So you can't just analyze the individual parts and then add them together to work out how the system will behave. Instead, you get these interesting emergent behavior from the second order and the third order effects. There are some limitations to simulation. In particular, there's the cost of actually building a model and the cost of validating it, because you don't really want to run with an unvalidated model. There's also the risk. If you make inappropriate modeling decisions, you could end up with something that's actively harmful. But it does have particular strengths. So specifically, simulation lets you reason about new scenarios where you may not have any other alternative. If you don't have data and there's no way to reason about this emergent behavior, then simulation might be your last resort. And also, once you built a simulation, it does scale nicely and give you some quite cheap experimentation. So I said complex systems. At Ocado Technology, we have quite a lot of complex systems. So as Tomek described, we do the whole of grocery e-commerce. So from the e-commerce part of customers interacting with our platform to place the orders, through to the supply chain of ordering the products that we need, fulfillment, how do we actually assemble these into the orders that we want to send to customers, and then last mile, actually delivering them. So there's complexity across a number of these, and so we have quite a number of simulations. So on the supply chain side, so supply chain is about ordering stock and customers buying it from us. The first order approximation of supply chain is really quite uninteresting. So if you're going to sell 1,000 of an item, you order 1,000 of that item. I see Ben's now got nothing there. But actually, when it gets really interesting is when you dive further along there. What happens when you have unpredictable demand? What happens when you have imperfect predictions? How do you analyze the second and third order effects to think about what the trade-offs might be between the storage space, how much buffer you have, and the kind of product availability that you're going to offer to customers? That's where we have a simulation to help us to understand what's going on there. On the last mile side, this is all about optimizing our delivery schedule. But actually, a lot of the optimality of this comes from which time windows we give to customers to receive their delivery. And that depends on the schedule that we've built up to that point. So you get this sequential decision-making and this emergent behavior over time. And it's very hard to reason about that in isolation. So we have a simulation where we can actually play orders going through, and we can see how the optimizer handles this and how the schedule builds up over time. On the fulfillment side, we have quite a few different simulations. So these range from physics-based simulations of particular hardware. We have simulations of people walking around a supermarket with a trolley picking customer orders. We even have a simulation of how we pack the items into bags as efficiently as possible. But the one that I'm going to cover today is our Hive simulation. So I'll give the details in a bit, but conceptually it's a high level. This is all about the interaction between hardware, algorithms, and layouts. And each of those affects how you should set up the others. So yeah, as Pavel said, I'm Rob. I'm roughly speaking a practice lead for simulation research here at Ocado Technology. What do I mean by simulation research? So simulation research in Ocado Technology, it's the name that we give to one of our data crafts. So alongside data analytics, data science, data engineering, we have a data craft focused on the use of simulation for insight. So what does this involve? This involves a lot of the skills that you would use as an analyst as well. So there are the technical skills. How do you actually get the data? How do you process it? How do you visualize it? So SQL, Python, whatever your tools of choice are. We have the business understanding, because it's important to make sure that you're actually answering the right question and delivering the value for the business. And then following on from that, you have the storytelling with data part, because people don't make decisions based on data, they make decisions based on stories. And the data comes in to make sure that you're actually telling the right story and that you can have confidence in it. But on top of that, there are some simulation-specific things. So developing appropriate models, with appropriate being the key word here. How do you design simulation experiments, which might not look like a classic A/B test, for example? And how do you communicate the nuances of this model? So this is another skill that's important in analytics, but it takes on a whole new level in simulation, where you've got these modeling assumptions could make a big impact on the results, and you need to make sure that whoever's making the decision really understands what the model is and what it's saying. So I'm going to talk to you about On-Grid Robotic Pick, or OGRP. I'll use that abbreviation quite a lot, which is these robots here. Specifically, I'm going to talk about our Hive simulation and how we use that to reason about the system behavior when we first developed and introduced these robots. So I'm going to start by talking about OGRP, what it is, and why we were developing it, some of the challenges that we had. Then talk about how we used simulation to help with some of these decisions. And then I'll end by trying to pull that out into a framework that you can use for how to apply simulation more generally. So let's start with why we're doing OGRP in the first place. So before I introduce OGRP, I need to give you some background. This is the Hive. So the Hive has three main components. We have the totes, which are these open-topped metal or plastic bins that hold the grocery stock, and they hold the completed customer orders. We have a grid structure, where these stacks of totes are stored. And then lastly, we have bots, which move the totes around the grid. Now, if you have one bot moving one bin around, it's not very complex. But when you get hundreds of bots picking thousands of orders in a large grid like this, it becomes very hard to reason about what's going to happen. So some of the sequential decisions that we have to face are: which customer order should we put next? Which stock tote should we pick from? Which bot should move this tote? Which path should this bot take? And then when we've picked it, where should we store this tote after use? And all of these will change the layout of the Hive. They'll change the paths that the other bots have to navigate around. And so you get this emergent behavior there. And because of the need to understand this emergent behavior, we actually developed the production control code in simulation. In fact, as a fun fact, the simulation is actually older than the production code itself. We developed the simulation, and then we built the production code inside it, rather than building the simulation around the production code. Another fun fact, so 278 years, that's how much Hive operation we simulated for analysis last year. And I say for analysis because it's not including the simulations that run routinely on every single commit of the production control code to test out certain scenarios and make sure that we're behaving in the right way. So it's all very well having a grid and having bots that can move the totes around, but we still need to pick the orders. So here's a quick overview of how this process works. So firstly, the bots retrieve the stock totes. They drop them onto a conveyor at a pick station. The tote moves along the conveyor. A person will look at the instructions on a screen. They'll take the right number of items out, and they'll pack it into bags for the customer. And then when we're finished with it, a bot will pick up the stock tote and put it away in the Hive, and it will do the same thing for the customer order when that's completed. It will be stored in the Hive until it's needed. So this is efficient. We think it's the most efficient online grocery picking system in the world, but the picking is still a large part of the overall labor cost of fulfilling a customer order. So what can we do about that? You can probably guess where this is going. It comes to OGRP, so that's these robots here. So they are on grid because they're mounted on top of the grid. They're robotic for obvious reasons, and they're pick because that's what they're doing. So now the bot can drop off a bin next to one of these arms. The arm can pick the items into the customer delivery, and then the bot can just pick it up from there without any human having to actually handle the goods. So that's where we are now, but developing OGRP was a significant challenge. So first, if we think about some of the things that OGRP as a product, as a robot needs to do, it needs to handle tens of thousands of different items. If you think about the range of things that you see in a supermarket, from bananas to bottles of water, it has diverse shape, weight, packaging. It needs to pack the items densely, quickly, and carefully. Again, if you think about your bananas and your bottled water, and think about what happens if you pack them badly. It needs to respond to unpredictable presentation of items. You can't just assume that everything stays in the tote in exactly the same place in exactly the right orientation. Things will fall over, packaging might have problems. So we need to handle all of these things. Next, things that we needed to do to actually get OGRP built. We needed to integrate a lot of completely new capabilities. There was some cutting-edge research into computer vision, into the soft manipulation side, and imitation learning, which I'll discuss briefly later. We need to ensure the bots work efficiently alongside OGRPs. So there's not much point bringing in new hardware if the rest of the system's going to suffer as a result of it. And we need to work out how to design efficient sites and how to install and maintain the OGRPs with minimal disruption. So the key thing is it's not just hardware development, it's not just hardware and software, it's not just hardware and software and algorithms, there are all these processes around it, and they all interact with each other, they all depend on what the decisions that you make in another place. So we've got to pull this together and deliver this project. So how does simulation help with a project like this? So if we think about how the OGRP product evolved, it started off as just a very high-level concept. And then gradually over time, we understood more and more about how the end solution was going to look until it got to the production system that we've got today. So a key thing about how we simulated here was we started early with a low fidelity simulation with just a rough idea of how it was going to behave. And then over time, we refined this alongside the product as we learned more about it until we get to the high fidelity simulation that we've got today. And this meant that we could start answering high-level questions from the beginning of the project, right down to the more detailed questions that we can answer today. So let's look at some of these questions and see some of the ways that we use simulation here. So the very first question at the very start of the project, is the concept of OGRP actually worth pursuing? I've talked a little bit about some of the research that went into this. There's obviously a lot of investment to get the product to where it is today. Is it actually worth that effort? Can we get an idea for how much we're really trying to gain from this? Now, when the videos load, if you look at the video on the left, this shows a bot moving across a normal grid without OGRP. So if you look for the orange bot entering from the left, you can see that it needs to move a little bit to sidestep some other bots, but generally it has a fairly smooth path across the grid. It can come up to a pick station, it can drop off a tote, and it can drive away, and the whole thing is relatively smooth. So we know that this works. We've built lots of sites like this. We're quite comfortable with that. On the right, this shows us with our OGRPs. Now, there's no orange bot, but just if you mentally look at the grid of OGRPs on the white cells, imagine that the cells around them are where they might need to move, then you're left with the bots traveling along much smaller corridors in between them. And you can see that the grid by eye looks quite a bit more congested. So we were fairly confident this was going to work okay, but we wanted to be sure. So what did we do? We already had our Hive simulation. We can add a fairly simple placeholder model of what the OGRP might look like, and we can use this to just get a sanity check. So it's a plausible scenario of how the arm might move, and we can see whether we get the congestion or not. So this is an example of using simulation for a proof of concept evaluation. So something completely new, you can mock up a quick simulation and go for a quick and dirty estimate of what's going to happen. An observation here is that it sounds like we're getting value from the simulation as soon as we built it. We actually started getting value from the simulation before we built it. So conceptual modeling is the process by which you actually work out how the simulation should behave before you start to, or while you're starting to implement it. So the key point is that by bringing together all these stakeholders, all these subject matter experts, and sitting down together and thrashing out in detail precisely how this should work, surface a lot of assumptions, a lot of inconsistencies, and it can help to drive alignments even before you've built the simulation. So we're going ahead with OGRP. What comes next? Next, we want to start developing the bot orchestration algorithms to work well with OGRP. So how should the bots and the OGRP interact with each other? So on the surface, our bots and our OGRP arms look quite similar. So they're both in-house hardware, they're both optimized for grocery fulfillment, but when you dig a little deeper, they're actually quite different. So if we start with our bots, they're very predictable, they're very deterministic. The key point here is that we could plan our bots hours in advance and we know where they're going to be to within a few milliseconds. But we can't do that with the OGRP. As I mentioned before, the OGRP needs to respond to what it sees in front of it. It needs to cope with this stock that has fallen over. So it's flexible, it's adaptable. We have this behavior cloning. So I talked before about our imitation learning. This is where you take human operators' behavior, and then you blend it with its own experience. And that gives us a technique that's very robust. It can scale to new products very easily. It's very fast, but it's not guaranteed how long a pick is going to take. So we needed to work out what the interface should look like between these two different systems. So what do we do here? Well, we've got the simulation in place. So now we can start to develop the control logic. So the team who are developing the algorithms can use the simulation, and they can build their algorithms against that, and they can get this very fast feedback about how it's performing. Here we're using the simulation for the feature development and testing, which is another use case where we use simulation heavily. And something to point out here, not only does the simulation give you this fast iteration and this instant feedback, and you can code something up and you can get the feedback straight away about how it performs, it also lets you start development much earlier in the process as well. So if we'd waited until we'd got physical arms ready to go before we started developing the algorithms, we certainly wouldn't have got to where we are today with OGRP. So everything's progressing now, including the bot orchestration algorithms. Great. What comes next? So now we start to get the more detailed, more precise questions about how the system should behave. For example, should we invest in a new camera system? So our original design for OGRP had a camera that looked something like this. So you can see the OGRP in the middle, and you can see that there are 8 cameras held on a little platform above it. And that worked fine, but we've got a grid cell here taken up by the gantry support. And that grid cell's in a good location next to the OGRP, where we think there might be congestion because we've only got a narrow corridor between them. So it would be great if we could free that up. The option that you'll have seen today in the videos earlier, if you were paying attention, or paying a lot of attention, is that we don't have that. We actually have a wrist-mounted camera instead. So this has freed up the cell. But before we started developing this, bringing together the changes for the computer vision system, the installation process, everything else, we wanted to know, well, is it actually worth it? There are a lot of things that we want to do. We want to get OGRP live as quickly as possible. Is it worth spending the time trying to fix this now, or is the benefit too small to be worth it? So what do? The simulations here are quite straightforward. It's just an A/B comparison of the two options. So you can simulate with the gantry camera, you can simulate without the gantry camera, and you can measure the benefits that that extra grid cell gives you in terms of the performance of the site. So here, we're using simulation for a strategic product direction. So it's a decision that's going to affect the long-term direction of where the product's going to go. Now, an observation to make here. The experiments don't need to match reality. So in this case, when we took out the camera gantry, in the simulation, that was the same as if we had the wrist-mounted camera. But say we wanted to think, what's the benefit of developing some algorithms that mean that the bots can move out of the way of the OGRP and it never has to wait for them? You could simulate with an arm that can move through the bots. Obviously, that's not a solution that we'll end up developing, but it can still give you some valuable insights to how the system might behave and what the size of the prize is that you're going after. What comes next? So next, we start to want to actually deploy these OGRPs. So how many arms do we need for our Luton site? So Luton was the first site that we built with OGRPs in mind. And this sounds like quite a simple question, but it's actually quite a subtle one, because there are lots of different levers that we can pull to try to get throughput from the site. We can add more OGRP arms. We can add more manual pick stations. We can add more bots. And as per everything I've said earlier, the interactions between these are quite complex. So if you add more OGRP arms, your human pickers are picking different items than they were before. If you add more manual pick stations, the bots are stretched more thinly than they were before. If you add more bots, well, maybe you want to recalibrate how the bots and the OGRP interact. So it's quite hard to reason about these trade-offs. But this is where simulation experiments can be quite useful. So simulation, all we need to do is we just try out all of these different hardware configuration options. Obviously, this is unrealistic if you've actually got to build sites with all these different configurations and test them out and sweep all the possibilities. But once you've got the simulation there, it's relatively cheap to do. So here is not a strategic decision that's going to have a long-term impact on the project, but it's a very expensive decision. So even though it's a tactical one, it's well worth running some simulations to make sure we're making a good decision. And the observation, I've already said, simulation experiments scale quite cheaply once you set them up. So you can go for the conceptually simpler analysis rather than the more data efficient analysis that you might do if you were analyzing production data. Okay, so we're building sites with OGRP, everything is going. Now we want to start really optimizing it. So the next question is, how long should we allow for OGRP picking? So as I mentioned earlier, the bots in the OGRP, they behave quite differently. And when we're planning the bots, we'd like to be planning them reasonable time in advance, but we need to cope with the OGRP responding to unpredictable events. So I'm going to try to talk through a graph here. This graph is showing a cumulative pick time graph. So on the horizontal axis, we have the pick time, and on the vertical axis, we have the percentage of picks that are less than that particular time. So let's say we want to make a provisional plan for the bots. We pick a time, and we plan the bots, and if the OGRP is done earlier, we'll try to replan the bots. If the OGRP is taking longer, then we'll definitely replan the bots. The risk is, if we plan the time too late, we might end up wasting time. If the arm might sit waiting for a bot to drop off a bin that it can't do any earlier. On the other hand, if you look at the arrows at the top, this many times, we're definitely going to need to replan the bots, at least in that local area. And there's a very real computational cost with this if you do it too often. So what can simulation do here? We don't have a perfect simulation model for this. In particular, the computation cost is going to be very different in a production system with real hardware than it is in a simulated environment. But we can try to get order of magnitude estimates, and we can try to reason about the shape of this trade-off and how it might behave. So here we're using simulation for optimization support. So you could simulate completely to optimize something and then just deploy those parameters to production. Here we're using simulation to inform the production experiments that we want to run. So even if you've got an imperfect model, these rough answers can still be very, very valuable. So lastly, it sounds as though everything is going quite well here, but being Ocado, things don't tend to stay still for that long. So the next question is, how should we deploy OGRP for non-grocery operations? So for this one, I'll need to introduce Ocado Intelligent Automation. So this is a business unit who are taking our warehouse automation technology that we've developed for grocery, and they're starting to work out, how do we apply this for non-grocery domains? So how do we provide this automation to clients like McKesson Canada, who are using our Hive automation systems for their businesses? There are some challenges with this. On the technical side, we have a wide range of different products. Obviously, grocery has quite a wide variety of products within it, but when you start looking at completely different industries, you see even more of a range. Each of these clients likely has different timings and different metrics. They also have other hardware and other processes that they need this system to work around. And you're not just trying to optimize the Hive in a well-understood environment that we're used to, you're trying to optimize across multiple interdependent systems. So should we move some of the processing out of the Hive to an upstream part of the system or to a downstream part? Should we split it in half? How should this look? There's also a particular sales challenge as well. We're speaking to clients who aren't necessarily familiar with warehouse automation at all, and especially not with Ocado systems. So how do you build the confidence of prospective customers in a new system that they've never seen before? So one approach is you can wow them with PowerPoint slides. You can give them big, impressive sounding numbers. Another approach, when it loads, is you can actually give them a visualization of a very specific implementation where they can see that there's nowhere to hide. This is how their system could look based on the assumptions. They can trace it through, they can see what's happening. So not only that, this is actually quite valuable for us as well on the analytics side. So there are certain problems that are quite hard to pick out from looking at a spreadsheet. But if you look at a visualization, you can see, oh, why is that bot waiting there for longer than it needs to? And you can dive straight into it. You can then cross-reference that and look at it in the data itself. Certain problems are much easier to see when you actually picture everything in front of you than looking at any number of statistics. So here, we simply simulate a plausible end state, and then we visualize it. And we're using that for sales support to bring the system to life for clients. And yet the observation is that visualization can provide a lot of low-level insight, not just the confidence in it. So that's how we simulated OGRP. So now let's take a step back and try to pull out the learnings for simulation more generally. A quick recap of what we've seen. We've seen the simulation use cases of proof of concept evaluation. We've seen feature development and testing, strategic product direction, expensive tactical decisions, optimization support, and sales support. And we've seen observations that conceptual modeling itself starts to drive alignment before you've even built a simulation. We've seen that the simulation lets you iterate quickly and also to start development early. We've seen that experiments don't need to match reality to be useful. We've seen that the experiments scale cheaply once you've got them set up. We've seen that even rough answers can be useful, even if you haven't got a perfect model. And we've seen that visualizing a simulation can give you quite a lot of low-level insight into what's really going on within the simulation. Now, before we pull this too far back, I want to just talk about abstraction more generally and to try to use a slightly more intuitive example here. So imagine you've got an area and you're tasked with creating a map for that area. What do? Well, the first thing you do is probably ask who's going to be using this map. If it's for motorists, you want to prioritize putting on roads, interchanges, driving distances, speed limits. If it's for tourists, you want to mark on the places you think they're likely to want to go. So where are the tourist attractions? Where's the public transport? Where do they go to find hotels and restaurants? If it's for a hiker, you want to have contours on there, you want to have footpaths, you want to have the landmarks that they can use to navigate when they're away from signage. If someone's taking a train, they don't actually care about any of that. All they care about is the connections. They don't really mind about the layout. You can imagine other use cases as well, once you include the geologist who wants to know about what's under the ground and the tax collector who wants to know about property boundaries and how productive each farm is, you get to something that's so complicated it's completely useless for anyone. So there's an idiom, the map is not the territory. What do we mean by this? We mean that the only perfect model is reality itself. So actually the whole power of abstraction comes from leaving out details to focus on what's important. Imagine if you're still doing maths and you've still got to 3 apples plus 4 apples make 7 apples, and you haven't abstracted out the 3 plus 4. It's a whole lot less useful and a whole lot more difficult for any maths you need to do. And the best abstraction depends on what you want to do with it. So simulation and modeling generally, this is an abstraction. So the same principles still apply. So all models are wrong, some models are useful. So this means that modeling is an art, not a science. There is no perfect model. You're always going to have to use your judgment to decide whether this is important or not and how you approach it. And the best model isn't always the most detailed one. It's the one that gives you the best insight. You might want a completely different model if you're trying to answer a question about the throughput of a system or the efficiency or the latency. So how should you think about a simulation project? So firstly, validate the need. Do you actually need simulation, or can you get away with a more robust, simpler analytical approach? If you want to progress, clarify the use cases. So like a map, if you're making a map without knowing who's using it, it's unlikely to be very suitable. The best model depends on how you actually want to use this and the questions you want to answer. Then conceptual modeling. So before you start jumping in and trying to write the code as quickly as possible, agree the model details, speak to stakeholders, subject matter experts, make sure you understand how this model wants to behave, bring the stakeholders along on the journey, and good practice to document it as well. Then you can build the simulation. So we build our simulations mostly in-house. That's because we want to embed production control logic, and we want these systems to talk to each other. But if you're building a one-off simulation, there are off-the-shelf and there are even open source tools available to help with that. Then check the behavior. So you've got a model, validate it, compare it to production. Play with it. Don't be afraid to sit down and just see what happens if you tweak this or tweak this. Visualize it and see what's happening and follow the path of things going through the system. And break it. You don't really understand the system until you've pushed it to breaking points. When you've got a simulation, you can see, well, what happens if I send this timing all the way down towards 0? Can I actually get this latency to go higher than this other factor over here? And then use it. And don't just think of it as a crystal ball, set up the scenario I want and see what the answer is. Think creatively about this. Think about the kind of experiments that you can design and how you can tease insight out of this model that you've built. And then rinse and repeat. So keep iterating through that as you want to answer more questions, but validate the need, agree it with stakeholders, and gradually augment the simulation if you need to. So a final thought here, and if you're taking one thing away from the talk, I hope this is it. The simplest way the most naive way to think about simulation is that it is a model. It's a piece of code that executes, that says, when this happens, then this happens, then this happens, and lets me see what happens as a result. But actually, there's no power within this piece of code itself. The power comes when you combine the model with the credibility, the trust that people have in it, the interpretation, so how do you actually make sense of what it's telling you, the experiments that you design, and the data storytelling that you actually provide from it. And so the simulation, the value actually emerges from the combination of all of these things and all the practice that you put around it to translate this model into actionable insight. So it just remains to say, if you want to know more about our technology, you can go here. You can search for simulation and find out how we simulated Ocado. You can search for robotic and find some more videos of OGRPs and some more information about that. You can also send me a message. My contact details are here, or I'll be around afterwards as well. Thank you very much.
Do we have any questions? I can see we have one at least.
Thank you. I have two questions. Thank you very much for the talk. So the first one is that this robot, there are two robots. One is picking, the other is transporting. So I believe that each one of them have a brain of their own. So my question is that when it comes to so many moving parts, so many robots working together, did you use some swarm intelligence like ant colony, or were you involved there, or it was not in your scope? So I don't know if that's a plausible question, but if you were, okay. So can you tell us something about the swarm intelligence side of this thing? And secondly, about the ROI, like how to sell it, because that's the most difficult part, because you can show a visualization and a lot of details, and then the customer would probably buy it. But again, telling the real business value or the dollar value, that's again always a challenge. So if you can tell us something about that.
Okay, I'll just try to backtrack. So the first question was about the bots controls. I obviously can't give too many details, but they are coordinated. It's not just completely independent bots going around. We do have this orchestration AI that's tracking all of the bots and making decisions based on what it knows about all of them. For the second question about the return on investment, so I guess as with any analytics, you need to answer the right question. You might be asked what's the return on investment, but maybe you can't answer that question, but you can answer, well, how much is it going to cost and what kind of throughput can we get? And you can then make it the stakeholders' responsibility to make sure they're using that information, they're pulling it together. And so that's generally the approach there. So we wouldn't try to get that from the simulation. We try to be very precise and say, look, the simulation is saying that based on these assumptions that you've given us, this is the throughput you can get, this is what it's sensitive to, this is how you can get an extra 10% out of it, this is how much hardware you need to have. But then it's more of a business decision to decide, well, what do I want to do with that? And so that's where we draw the line.
So the how part is very beautifully handled by the simulation. But when the money will come, that's... So there is like, we need some business acumen to sell that wonderful product that we have developed, right?
Mm-hmm. Yes, but again, I think that's where salespeople come in and understanding the customer's needs, working out what the right system is for them. And I guess I'm being on the data side myself. My role is very much, look, can we answer this question? Can we make sure that we're giving you the right data that you need to support that? So I think hopefully that's helped a little bit. If not, then that's probably about as far as I can say, I think.
Cool. Thank you.
Do we have any other questions? Okay, there is one.
Full disclosure, I'm from Ocado. Rob, a question to you. At some point in our team, we were thinking about simulation-driven development. So you mentioned one of the use cases for simulation, kind of validation of the features developed. And we were thinking about whether this would be possible to actually use simulation as a driver for specifically for complex systems, supply chain optimization, last mile optimization, things like that. So how far were you able to go with this kind of a concept of using simulation to validate features being continuously developed, because it's about continuous development of features. So many teams working on different parts of the system, so emerging behaviors actually happening all the time. So could you share something about that?
So the bot orchestration systems that I talked about, I said they're developed in simulation. So when you're writing software, you often have unit tests to test particular pieces of functionality. We actually use the simulation in that kind of vein for a lot of things. So if you're trying to simulate an emergent behavior of the system that says, when this error is raised, then I should fetch this bin and I should take it here. And when this flag is then cleaned on this, I should then take it up and move it here. That kind of behavior is very hard to have in a unit test, but you can have these very cheap, lightweight simulations there. So actually those tests are written alongside the unit tests as we're developing this. So the whole production code is developed with this suite of tests there. I don't know whether that's quite answering your question or not, but that's what I think of as almost a simulation-driven one. So you can write the simulation first, you can check that it fails, and then you can fix it. I don't know how the developers actually do that.
Our kind of conceptual model that we would write a simulation first, or we actually had a simulation first, and as we were writing features, we were thinking about how to kind of embed them in a simulation model so they can be actually tested as they were developed, what kind of emerging behaviors they were causing.
Yeah. So in terms of proper simulation-driven one, I don't know, to be honest. My guess is that, like with test-driven development in software engineering, it's something that sounds good in practice, but you have to be quite disciplined to actually go ahead with it. And I imagine there are cases where people will add the test afterwards, but maybe wish they hadn't and wish they'd done it earlier. And so yeah, there's a discipline involved there. I don't know about how I can answer that exactly. I can help to put you in touch with some people who can, though.
Well, this is why we have not done that in our team. That basically it was more complex organizational than conceptually. So that's why we kind of gave up on it. Thank you.
Okay. One last question, if there is any. I can't see anyone quickly, so let's stop with that. And thank you very much, Rob, for this performance.